There we go. Okay, so share my screen again. Okay, so first off, we're going to start with, I think most of you have seen questions like this before. There's almost certainly going to be one like this on it. So I'll try to go full screen on this thing. But I think what we'll do is we'll take 5 minutes, like five minutes each question, and then we'll go over the answers, that type of thing. So my screen's going to be cut off a little bit, but you're basically just going all the way down for 6, 7, 8, 9, 10, 11, 12, 12 values, all in little endian and big endian. How do you go full screen in Microsoft Word? There we go.
Oh yeah, I'm just curious because there was a similar question like this in our lab, and we had to big endian and little endian referred to how the information was being stored, but to do the question, we actually had to assume that our machine was always going to be reading in little endian. Otherwise, nothing would change for value-wise.
Well, it's oh my god. What do I mean with the formatting? Well, it's sort of the same thing. So yeah, it's sort of the same thing. Like if you read it and then manipulate it and then store it, it's going to be the same as well. No, I mean there's only one way to do it. I mean, well, let's say that we're just going to be storing I at 1,000. So little endian, it's going to be yeah. So little endian, it would be just like OD, FO, ED, FE. And for big endian, it would be FE, ED, F0, 0D, right?
Yeah, but if the little endian one read in little endian, we'd get this, we would get feed food back. And then if big endian read in big endian 2, we'd get feed food back. But like in that lab question, you had to assume the machine was reading both in the same little endian way so that you get different results.
I see what you mean. Yes. Yeah.
Doesn't the machine always read from the lowest register though? So it doesn't like read in big endian or read in little endian. It reads how it's stored from the lowest register, and little endian stores it differently than big endian, right? Like if you think of it left to right, the machine always reads from memory left to right, but little endian, big endian store it into memory differently, right?
No, it definitely reads it too, because if you
Okay.
have a value, it would put it or maybe not. If you guys took the lab a bit earlier than me, then you know better. I did take this course a year and a half ago. Yeah, but just to clarify, they would be reading it in the same way. Yeah, because you're right. Otherwise, they would just be reading it backwards and then flipping it and then putting it backwards. So it would be the same. Okay, so let's go over this. So let's start off with the easy one. So for these four, we're just going to be assigning it feed food, right? Because if you look at the rest of these, we're not actually going to be changing I ever again. So for big endian, this is going to be FE, ED, F0, 0D. And this guy is the same thing but backwards. 0, ED, FE. Right? Does that make sense? I think that's pretty straightforward. The next one, actually, why don't we go to the last one, because the middle one is the more confusing one. So J is going to equal, so the value of J, so we're not dereferencing, the value of J is going to equal the address of C0. And the address of C0 is 4 bytes away from int I, so it's going to be right here. So it's going to be right here. So the value of J is going to be 2014. So because it's signed, you would have to fit either zeros or Fs to pad it. But in this case, it is a 2, so we're not going to be padding with Fs. So this is going to be 0, 0, 0, 0, 2, 0, 1, 4. And likewise, for little endian, it's going to be 0, 0, 0, 0, 2, 0, and 1, 4. Does that make sense?
I'm just curious, how did we, I guess, are we first, is the convention to first assign the integer in the memory and then the char?
What do you mean?
Like, I'm not sure how else are you getting the address of C of 0. And the only way to get that would be to say that C of 0 is stored at 0x2014.
Yeah, because that's right here. So we have int I, and int I is stored at, where does it say? So I is stored at OX 2010. And so naturally, the next place in memory is going to be OX1, 2014.
Okay.
And so J is at 2018.
Okay. All right. Thank you.
So does that make sense? We're storing the value of C into here, and the value of C, which is a pointer, is the address of itself. If it
Why is there the gap? Is that,
I was just doing the two easy ones first because the middle one's more confusing.
oh, so it's, sorry, which line are you doing then?
I was doing this one.
Oh, okay. So why did that one go from, like, I would have thought it would have gone into 2014,
It is.
like right after.
2014.
Yeah. Why is there a blank between 2014 and 2017 then?
Because we haven't done it yet. We haven't assigned. We've assigned places in memory for these places to be, but we haven't assigned a value to C yet. But we did assign a value to J, but we haven't assigned a value to C. We're saying that J equals the address of C, and the address of C is OX 2014. So we're going to be putting 2014 into memory where J is. So this is J, right?
It's because
Why-
they're
why is
assigned
that
in
J?
order. It's because they're assigned in order
They're assigned
from
in order, yeah.
2010. So it's 4 bytes for I, and then a char is only 1 byte, and then we have an array that's 4 of them.
Oh, okay. So
And then,
you're going
yeah.
in, sorry, you're going in the order of the stuff on the left, like the int char.
Yeah, exactly.
Oh,
Like-
okay. Sorry, I thought it was you're doing it in the order of operation in foo.
No. This is the actual like blocks of memory that they're going to be stored in. So I am doing this in order of operations. First, we're going to store this in I, and then we're going to store the address of C into J. So we are doing this in order. So now we're here. So now we're
Yeah, I'm thinking more in physical order though. Like the int char int on the left, like we think of that as a like kind of a struct as we would a struct.
Yeah, exactly.
Okay.
Yeah. Okay. So now we're going to say that C0 equals I shifted 8. So what does that mean? So let's start with the little endian because it's makes a little more sense. Let's put in so let's put it in what it would be in the intermediary. So if we're shifting it right by 8 bits, sorry, not bytes. If we're shifting it right by 8 bits, then this is going to be, where am I on this? F0, FF, FF, and FF, because we're shifting it right by 8 bits.
Isn't the C of 0 char? So don't we want to, we'd want to, I guess we're removing 3 of the bytes, so it's only 1 that we're storing.
Yeah, you'd think. Let's see this. So because we're shifting right 8 bits, we're going to be taking this guy here and then storing it in the C position.
Mm-hmm. Yeah.
And then just filling the rest of these with FFs.
Are the FFs from the signed part of it? Like because it's signed, it's filling in to the left?
Yeah, exactly. So yeah, this is kind of weird. So we shift I right by 4. So we're taking F0. And then you're right, it's just a char. So we're storing F0 in the C's position. And then we're padding the rest of it with F's.
Okay.
Actually-
Is the padding just a convention?
No, sorry, we're not actually padding it yet. That we're going to be doing that in the next step. No, it's not convention.
Or sorry, I can actually, yeah, I can see that because we would need to do the padding later because when we dereference the object, we cast it to an int, so you would be, when you're extending it, it would be a signed extension, so there would be f's.
Yeah. So I jumped ahead. I jumped ahead one step. So yeah, we're just storing something into C0. So that's going to be there. And then star j, and remember j equals the beginning of C, right? So when we're dereferencing j, that means we're putting something in putting something in here, and j is an int, so we will be filling all of these. So it's going to be the value of I, or change to a pointer, star C. So
Wait, is that also I, or sorry, also j inside that? Like dereference j equals dereference j or int
oh,
cast.
sorry, say it again.
Is that also a j on the inside as well? On the left side of the or?
Yes, j. I was just looking at that. I was thinking that was an I. I'm like, that doesn't make any sense. I is not a pointer. Okay, so if we,
How do you put the asterisk beside C? I thought C was like a char array. I thought the dereference only worked out on like pointers and stuff.
yeah, you'd think. So what is C? The value of C is 2014, right? So we could cast that into an int. Then it would be FFFF2014. That's weird, right? Oh, sorry, 00002014. It's weird, right?
Mm-hmm.
That's what C does. So we're gonna say that it's C, so 00002014, or the value of J, and the value of J is just these. But because we've cast this to an int, now we're gonna pad it all the way to the left.
But sorry, is C 2014 or is it FO in this case? Because
No,
2014 wouldn't allow you to do FF padding, would it?
Sorry, you're right. Yeah, you're right. Sorry, that's my mistake. Yeah, so we're actually taking the value of the C. I missed the dereferencing here. So we're dereferencing C. So we're getting F0. Well, FFFF0, and we're also dereferencing J. But they're the same thing. So then because we're casting into an int, we're just going to pad these with Fs. Make sense? Sort of. I know this stuff is extremely weird.
Yeah, would it be okay if we don't actually put the f's in the memory, but we just take out the F0 and then we sign extend it when we want to cast it to an int?
Well, that's exactly what you do when you do cast it into an int. If you have a char that's FE, and then or F0, whatever, and then you cast it to an int, now it's FF, 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 F0.
Okay, all right.
Okay. Oh man, we gotta get moving. We're spending a lot of time on this one. Okay, so I'm just gonna give you the answer for this one. So this one is FF, 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 unknown. So C0 equals I shifted right. So we take, again, F0, but this time we're going to pad it the other way. So F0, FF, 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 and then we're going to do the OR again.
Okay.
In the interest of time, I think we've got to move on because there are 8 questions, and we spent a quarter of the time on the first one. So why don't we take 5 and just do question 2? Let me move this down a bit.
Will this be posted after? Because I think the first question is actually really good. It's way different from the practice examples seen.
Sure. Yeah. Well, I'll have to think about it because I'm not exactly sure I would be allowed to. But yeah, hopefully. Should be 3. Oh my God. See, the formatting's terrible here. I'm sorry. Okay, let's start with here 2A 2B. Oh my God. Yeah, dec R1 is valid command. All correct. Okay, so let's go over this one. So just a little bit about assembly that I always try to do. I think it's a really good idea to load your values first. So I just like loading, because if you know that you're going to be using I, A, and B for the entire, well, this one's pretty short, but if you're going to be using it for the entire operation, like an entire method, you're gonna be referencing these multiple times. So it's good to start these as you. Oh, sorry, that should be an R. Start these as your initial registers, and also make sure that you're commenting what exactly they are. So a lot of people like they might say R0 equals I. It's not I, because I implies it's the value of I, but this is actually the address of I. So if this is a pointer, then you would say if you dereference it, then you would say it equals I. And then if you dereference it again, then it would be the value of I. It gets very confusing when there's pointers, and sometimes you have double pointers. It's a whole thing. Okay, so we've got I, A, and B loaded in here. So we're going to want to load, that's going to be really annoying. Load R0 into R0 because we actually want the value of I because it's just an index. So now R0 equals the value of I. So what we're going to be doing is storing the value of BA1 minus 1 into B1. So we're not actually going to be storing anything into A, so we can immediately load the value of AI into A's register. So we're going to be loading R1, R0, offset 4 into R1. So what this does, now we have R1 equals the value of AI, right? With me so far? So B is a pointer. So here's where you where a lot of people have issues. A lot of people would miss this next step, and it's very important. So if you try to store the value of whatever value you have into B right now, well, B is actually a pointer. So you actually have to load it to get the array that it's pointing to. So let's load R2 into R2. So now we have R2 equals B, the value of B, which is a pointer to something else. Okay, so now we have R1 equals B, AI. No, sorry, R1 is the value of AI. So now we're going to load, it's going to be R2, and we're going to be AI spots away, so R1, and offset 4, and we're going to load that into R1. It's okay if you do steps out of order, as long as they make sense. Like obviously you have to load the value of I into R0 before you can get that. You can use it for an offset. But yeah, like there's some things where you can move around. It doesn't matter. Which are you talking about? This step right after this one?
Oh no, for the R2, like, is it okay if, I know you wrote B, but could we also write, I mean, because technically, I guess we can assume it's an array. So it's like pointing to the address of the first index of that array,
yeah.
The address of B of 0.
Yeah. Yeah, just like this would be address of A0. That's the same thing. When you have an array, you're always assuming that if you have A, you have the first value of A. Or sorry, if you have an array, you have the first value of the array.
Will
So
they care if we do registers like, register 3, 4 instead of reusing them whenever possible?
No, but you want to get into the habit of reusing your registers, because otherwise you're going to run out pretty much immediately, especially in the later assignments. So this one's going to be B of A of I, and now we're going to decrement. We're just going to decrement R1. So R1 equals B A I minus 1. Now we're going to do a store. So what we're going to do, we're going to store R1 into, is it BI? Yes. Okay. So we're going to be storing it into R2, which is still B0. We haven't overridden it yet. It's going to be R2. It's going to be I steps away. So we have R0 as I, offset 4. And that is BI equals BAI minus 1. Does that make sense? Any questions? So here's a fun part. What is the minimum number of memory reads required to execute this statement? This one's always tricky. So let's start. We're going to be loading I. So that's 1. So this, yeah. So so actually getting the address of I into a register is not reading it from memory. But when we do this, we're actually reading the value from memory. So this isn't a memory read, but this is a memory read. So we have 2 right here. We have we're getting I, and then we're getting B, and then we're getting B.
So reads do not count as stores. So, if we're reading from an address, it's different from wanting to store to that address.
Yes.
Okay.
And then we have another one right here, because we're loading this. Oh, and missed this one. So we're reading A offset I. We're reading B offset 0. We're reading B offset AI.
Oh, I think the number of
Yes,
memory reads
yeah.
is for the statement below.
Sorry, sorry. I just realized that. We're actually on the same page up until right now. We're doing all the same things. So we're going to be reading the value of I. We're going to be reading the value of BI. We're going to be reading the value of A0. We're going to be reading the value of BA0. So that's 5 altogether. So first read is B. Second read is I. Third read is BI. Fourth read is A0. And fifth read is BA0.
And just to confirm, the only reason that we're doing B as one of them is because it's a pointer, right? So we have to access its value, and that's why we don't have to do A.
Yes, exactly. These things are very confusing. Basically, like I think there's a quick way of explaining it. So anytime I don't know if you guys can see this too well. First one, this is A, right? A is just pointing directly to is pointing directly to an array. So basically, if we do a read when we jump over. So if this is A right here, then we're going to be reading the value of A, and we're basically like hopping over this into the array. So that's one read. But B is a pointer here. So we're actually going to be stepping over twice, because first we have to read B, because if this is like OX 1000, like the value in here is going to be OX 1000. So if we have B, we do one read to get the value of the array that it points to. So it's OX 1000, and then we do another read to actually read whatever's in the array.
So when you grab the address of something, that's not considered a memory read?
No, no. Because you're storing that locally, right? Like at the bottom of your assembly function, you'll have all those printed right there. So that's actually not a read from memory. But then if you use that to read from memory, then it is memory read. Yeah. So yeah, Claire. Then I didn't read that, but you did get it. And yeah, sorry for confusing you guys. I misread this. Feel free to jump in and correct me if you ever noticing I'm doing things wrong. This is supposed to be a 3, but whenever I replace it, it's all weird. Whatever. Okay, so you know what? Let's just go with this. Okay, so let's do a little more assembly with these structs. Let's take 5. I'm gonna have to be going through these pretty quickly if I'm gonna keep this to 2 hours, but I don't have anything to do, so I can stay longer if needed.
Is that struct A contains struct B and a char array of C2?
Yeah, sorry. Let me.
Okay.
Jesus Christ. What is happening? Okay, you know what?
It's okay. You can type in the chat like what the components are.
I had to do this for a few other questions. I didn't have the actual midterm. I just had the solution, so I've had to go in and edit all these. There we go.
Oh, excellent, excellent.
Let's. Okay, let's go over this one. If you guys need a couple more minutes for the assembly, that's okay. I'll give you a couple more. But let's go over these struct sizes first. So size of struct A. So remember that pointer's 4 bytes long. So first off, you should go and find the largest member of the struct. So here we have char array. Okay, so that's size 1. Well, size 2, but each char is size 1. Int array, size 1, but there's 2 of them, so it's size 8. Struct B, that's a pointer, so that's 4 bytes, and we have a char at the end, which is going to be 1 byte, but padded to 4. So char, so that fills 2 chars, fills the first spot, so that makes 4, because we have an int next. Then we have 2 ints, that's 12. We have a struct pointer, that's 16. And then lastly, we have a char, but we have to pad it fully out, so that's 20. For struct B, we actually have the entire struct inside of it, so we know that's 20 already. But the max that it's going to be is the max size of padding that you're going to do isn't the size of the struct itself, it's the size of the maximum value in the struct. So here the maximum value is 4, so it's going to be likewise over here. Plus we have an int down here, but it's good to check because if this was 8 bytes, this struct B pointer right here, then we would be padding by 8 bytes over on this side. But it's not, so we're not. So 20 plus 4 for the char, padded for 3, plus 4 for the int, so that's 28. So offset of struct AD1. So we're not talking about, so just remember that that it starts at 0. So the offset of C0 is 0. Offset of D0 is 4. Offset of D1 is 8. So offset of struct AE. So we're offset 0, offset 4, offset 8, offset 12, offset 16. So this is where it gets a bit tricky. So struct B, the first value of struct B is the struct itself, and also this struct, and also this char C0. Does that make sense? The very first value of struct B is going to be C0 because it's not a pointer; it's directly in there. So if you're going A.C1, that's only offset 1. Struct B and X. So we have, to get to here, we have to jump 20. So char Y is offset 20. And then int X is going to be offset 24. Do you guys need a couple minutes for the assembly?
Yes, that would be excellent.
Okay. Let's give 3 minutes.
Oh, just to clarify, the B of 1, right? Because it's like A in struct A, B of 1, and B is a struct pointer. That's going to be an array of structs, like just a big block of. Okay. Excellent.
Yeah, that's right. Okay, we're halfway through our time, and we're on question 3, so we gotta hurry up slightly. So let's start with this guy. So if we look at this entire statement, easy trick. If it's on the right-hand side, we're not going to be storing a value into it. Like we're only going to be using b over here, so we can just load the value of this the value. Oh my god, the value that we need into this right away. So we're going to be loading R0, 0 into R0. Now R0 equals the value of A. Now we're going to get B. So we need to.
And I have a question. So since A is not a pointer, why do we need to get the value of A here?
I was actually just looking at that myself. Well, because the reason is, if you have, well, it's the value of A is the struct. So like if you have just like a regular int I, then if you load I into R1, then that's still the address of it, right? That's R1 equals the address of I. You don't actually have the value of the integer. But if you load it again, then you actually have R1 equals I, the value.
Yeah.
So you do need to load the value. Oh my god. So you do need to load the value into it before you can access it, because otherwise you're just playing around with a piece of. Otherwise, it's just like OX 2014 or something.
Yeah, so that's what I thought we were doing until the end, because we're getting b of 1.x of A.
Well, if you don't load it, then you're going to be trying to yeah, like you could do it differently. Like you could do an offset load right here to get the pointer to B, or you can do an offset load right here to get the first value in B. So if we do an offset load here, that's basically saying that we're going to be jumping from a point over here directly to right here.
Yeah, like I literally just did like A and R0 and then offset of 64 R0. So I thought that would be like all the way to the X.
No, because struct B is a pointer, so you need to load it. So you would actually need to do offset 12 and then offset 52 to get to X.
Oh, okay.
If struct B was directly in here, not as a pointer, then you'd be right. But first we have to get this value, and then load it in here. So there's 2 ways of doing this. First way, like you guys are talking about, we could do R0. Well, then we would have to load. I guess we could just do load 12 R0. Then R0 is going to be equal to B, the address. Because B is a pointer, it's going to be the address of A.B. Let's say we're doing it this way. So we're just going to load A into A. Now we're going to do an offset load, 12 R0. Now R0 equals A to B. So now we're right here. We're right at the top of the struct here, which is the top of our struct A. But we need to access X. So what we need to do is just completely skip all this and go straight down to X. So we're going to be loading 52 R0. Now R0 equals A to B dot X. And that's a load. So now we actually have that value in there.
And the 52 is that's like a complete skip of the 0th, B. So just 28, and then you skip A, which is also 20, and then a 4. If that's, let me check. Yeah, wait, so is that why our offset's 52?
Why is it 52?
Because we skip, I think it's, we're skipping like B.
Skipping struct A, which is 20.
Yeah.
Then we're skipping char Y, which is 4. Shouldn't it be 24?
Hmm. Wait, because I thought if it's B of 1, that would imply that you have 2 things in that array.
Yeah, this might be yes. Yes. Thank you. You're right. Okay, so yeah. So yeah, B is yes, you're right. Okay, so right here we have the first value of B is 0. But what we want is B1. Yeah, thanks. So yes, that makes sense. So we're skipping an entire struct B, which is size 28, as you remember. And then plus we have to skip another 24 to get to B1.x. Yeah, thanks for pointing that out. Does that make sense? You guys don't have to talk in the chat. You can just like yell at me. That's fine. Interrupt me, because otherwise I make mistakes. So yeah, first, let's just go over this really quickly again. We're going to load the value of A into R0. So A, now we're pointing at this first member. Then we're going to do an offset load to load the first value of B0. But B is actually a struct pointer. So this is A to B. So it's a struct array. Can you guys see this?
No.
So you couldn't see the last time either. Okay, basically, God damn, I wish I had a whiteboard. So basically, B is a struct array. So we have to skip over the entire first struct and go into the second struct, which is B1, and then load X off of it. So because it's all contiguous, because it's an array, we can just skip over. We can just skip directly to the X. So that's why we're doing an offset of 52. Because one size 28, and then we're doing an offset of 24 to get to int X. So now we have A to B1 dot X. So now we're going to do a shift left operation to 0. And now we've got our value. So now the only thing we need to do is store it into B. So load B into R1. R1 equals the address of B. Now, mind you, it doesn't necessarily say here, but it doesn't say B is a pointer. So we don't have to do another load. So now we're going to store our value, which is R0, into offset 24 because we're storing it
In X.
Yeah, so we're storing it into X. So we're gonna be offsetting 24 to get X. So now B.X, which is the same thing as B0.X, equals A. I think I copied and paste this. Shift left 1, 2. Okay. Anything you guys want to go over before we move on to the next section?
All right, I have a really, really quick question. So basically, anytime we see an arrow, it's just an indication that we're going to have to do a new load.
Yes.
Okay, cool.
Okay, static control flow. Oh God, this is going to be. Why don't we skip this one and go to the end, because.
Oh yeah, I don't think we cover this stuff yet.
That's the answer. It's gonna take a while. Oh no.
No.
Control flow isn't on the midterm.
Yeah, we just started like 4 loops in class.
Thank God. I really hate going over this with people. It's kind of a nightmare. Okay, question 5. C pointers. This stuff's super fun. Fun, I mean fun for me. Oh Jesus. I'm gonna have to copy and paste this again.
Is the midterm usually like time pressed? Do most people find it time pressed?
Yeah, this is the midterm that I actually did when I was taking the course, and I finished it, but not many people did. It was very time crunchy. Okay, so B just goes down, and it basically just gives you as many values as you need. Just so we're just listing all the changes that are going to be made. Let's take 5, get as many as we can, and then go over the rest. Actually, we're doing pretty decent for time. So why don't we take as long as we need. Also, when we're doing something like so we're saying like C of B of 1 equals 7. So you should actually be putting what the value of B1 is here. So like if it's C, it should be like C3 equals 7. It shouldn't be like, you shouldn't write B1.
Sorry, what does the -2 do? Where for the second line?
So the funny thing about C program, not the letter, is that it doesn't care about indexes, right? So if you had an array of length 4, you can access the value of the array of index 100. It's going to be completely unpredictable because it could be anything, but you can do it. So this is saying basically we're going to B wherever B points to, and then we're going to be minusing 2 of whatever type of it is. So B is an int, so we're going to be minusing 8 bytes and delivering whatever piece of data that is. Or in this case, we're going to be storing A0 in it. How you guys looking? Good to go over it, or need a couple more minutes?
Yeah, just like another minute or so.
Okay, so let's go over this guy. First off, what's the value of B?
3008.
So why is it 3008? Let's see. So we're starting off with B equals the address of C4. So that's going to be this guy, offset 4. Then the next time we're changing it is we're seeing B minus A1. Now A1 is 3, but we're not actually going to be minusing, or we're not subtracting 3 from it. We're actually subtracting 12 because it's a pointer, so it's 3 times the size of it. So we're basically shifting 3 spots. So now we're at 4. Now B equals B plus 1. Now that's this. And the address of C is 3000, so it's 3000, 3004, 3008. OX. Never forget your OX, because otherwise you can mark it wrong because it's a decimal.
Wait, I don't know how I got that right because I misread. Actually, maybe not. C of 4,
Oh.
It's the 10. Oh, okay. Because I was thinking of it as the 8, but because like you'd include the 0, but I guess not.
Well, you definitely start with 10, and then you minus 3. 1, 2, 3. Now you have 4, and then you add 1, so you get 6. And then B is going to be the address of that number, which is 3008.
Okay.
So let's go over things that we changed. Let's start with A. Actually, A's start with C. Actually, no, A's simpler. So A 7 is changed. So what is A7 equal at the end?
Wait, where does A of 7 change? Oh, and the A of C of 1.
Well, actually, I guess I should back up a little bit. So let's manipulate this. So first off, B is pointing right here. So we're saying B of minus 2 equals A0. So overriding 6 to be 1.
Mm-hmm.
Then we're saying B equals B minus A1. A1 is 3. So now B is pointing right here. C of B1 equals 7. Yeah, so C of B1 equals 7. B1, so B's right here. So B1 is 1. So we're gonna, I guess we can write that here. C of 1 equals 7. And now we're saying A of C1 and C1. Oh God. So I'm trying, this is confusing.
Well, I guess C is still pointing to the beginning. So C of 1 is just 4, I think.
Oh, and we're writing it to 7. Yeah, okay. So C of B1. That's what I did before. But A of C1.
So A of 4, I think. It's the...
Yeah, maybe they made a typo, but they're saying A7 equals B2. That's... let's skip this one for now. Let's come back to it. We're dereferencing B plus 4. So B points to here right now. So B plus 4, 1, 2, 3, 4. So that's 0, 1, 2, 3, 4, 5. And we're writing that to 6. So C5 equals 6. And lastly, B equals B plus 1. So now B is pointing right here. And now we're saying we're dereferencing B to equal the value of B plus 1. B is 2. So overwriting this to be 2. Oh, you know what? I didn't overwrite this. That's why. So C of B1 equals 7. So that equals 7. Okay, that's where the confusion is coming from. I didn't overwrite this. So in this line, we overwrite C1 to be 7. And now we're saying A of C1. So A7 equals B2. B2 was pointing here, and it's 8. So A7 equals 8. Sorry, I mixed myself up for a sec. And that's it. There's nothing else that's changed. Does this make sense? Anyone confused?
I guess the first part, when it's like C of 4, it's referring to the fourth. It's the fourth value. So in C,
it's not the fourth value. It's the fifth. It's the fifth index. Okay. Index 4 is position 5. So 0, 1, 2, 3, 4, right?
Okay, but it's still I guess it's still the address is 3016 because the first one is just 3000.
Yeah. 4, 8, 12, 16. Yeah, that's right. Any questions about this? So actually there was 2 questions on here that's about static control flow. So we're gonna have some extra time, I think. But let's move on to the next section. So let's do these one at a time. So basically, we're trying to find any bugs in the code and what's going to occur. So let's just take like 1 minute each and try to figure it out on our own, and then go over it. Whoops. Oh, no, it's fine. Okay, so what's the problem with this first one?
Your malloc is in a different, I guess, module. You're also not returning a pointer. So.
Yeah, we are. This is a pointer, and then we're returning R, and this is in star, and then we're returning the value of it.
Oh.
But yeah, the problem is that, well, does anybody know the problem? Don't say it all at once.
Really?
Memory leak, yes, because we're mallocing a pointer, and we're never actually freeing it.
But,
And
but
yeah,
aren't we
it
returning
is-
it to our? We're returning it to the function call.
Yes, but you can't necessarily trust the fact that it's going to free it after it's done with it.
Oh, okay.
So like
okay.
just this right here, there's a memory leak. Okay, let's do this next one.
But when you exit it, is it because this call process is also returning it to something else? I just don't see how this is a memory leak.
Well, because we're mallocing it and we're never freeing it. So when we're
We're
done with
returning the to its call, so we still have the pointer like that is pointing to that memory block.
yeah, but right here it's a memory leak. So you can't assume that some other code is going to fix it. Right here, there's a memory leak.
In the extract, in that.
Yeah, like with these two methods combined, you end up with memory leak. Oh, actually, sorry. This isn't actually returning a pointer, so this is always a memory leak because we're returning the value of R. We're not returning the pointer, so so whatever calls process can never free the pointer. So this is always 100% a memory leak.
Oh, okay. Actually, that makes sense. Yeah, because we're okay.
Yeah, it's more of a best practices thing to make sure that your memory is freed, and because yeah, like if you were returning R, you could free it in that other thing, but it's best practices to make sure it's not like that. Anyway, so this next one, have you guys taken a look? So the stuff in bold is new lines that have been added in. So anyone know what the issue is?
Dangling pointer?
No. Wait, remind me, what's the dangling pointer again?
It points at something it has no control over,
Yes.
like it's been freed.
Yes. Right.
Because I think you get the pointer back from extract, and then you set another pointer to that value, and then you free that value, but you just freed the value that you pointed at.
Yeah, exactly. So we have, so we're assigning R. We're saying star R equals extract. We're getting this pointer over. We're assigning it to a new name. Basically, we're freeing that name, but both T and R are pointing to the same thing. So we're freeing that piece of memory. Now we're trying to dereference it to return the value, but we can't do that because we're referencing freed memory. So yeah, dangling pointer. Next one. Does anybody know what's wrong here?
Ideally, you'd want malloc together where you're freeing it, but I don't think there looks like any issues because we store the object, we dereference it and store it locally before we free the pointer.
Yeah, so this actually runs fine with no errors. So there's nothing wrong with this code. Other than, yeah, like malloc and free are in different things, but it's okay. There's no errors. Okay, 6D. Anyone know what's up with 6D?
We're only working the stack though. So do we not, is calling free on R necessary?
No, it's not.
So if you declare int star r on the left side, and then you return it, but that was defined locally, wouldn't it? Hand it back, and then you've got dangling pointer.
Yes, exactly. So A is already established here. And basically, it's trying to free memory that was not allocated by malloc. So we haven't explicitly mallocked it, so you can't free it. Because what if you were passing it into process, and then you want to use it again after you use process, but it's been freed. So yeah, the problem is that we're freeing something that hasn't been explicitly mallocked. Does that make sense?
Do you actually be allowed to free it? What's the opposite of a memory leak?
In this context, it's actually kind of tough to say because C does really weird things sometimes. Like sometimes it just does stuff. Like if you have an array, you can access stuff out of the array and that's fine. It'll return that value. There's no problem. It'll do exactly what you tell it to. In this context, I'm not 100% sure. My best guess would be because you're freeing that piece of memory. Now int star A, so let's say A points to, well, A is an int pointer, so let's say it's pointing to an array. Now you have one piece of memory that's being freed in that entire array. So if you go to use it again, there's potential for accessing something that's already been freed. So yeah, like it's could end up with a dangling pointer. But on the other hand, if this program was smart, it would realize that, hey, you're trying to free something that you haven't mallocked, and it just wouldn't do it. So in the context of C, it's tough to say, but basically it's bad because you can't free stuff that you haven't mallocked.
Also, sorry, where's the dangling pointer? Is that?
Well, if let's say that we're passing a pointer into A. Now we're freeing it. We're freeing it right here because we're saying R equals whatever I is an offset of A. So we're freeing that piece of memory when we shouldn't have been because we haven't mallocked it. But let's say we have we've established an int, and then we're passing the address of it into process. Now we're freeing it. We haven't mallocked that. So so in that case, if we just have like a local integer and then we try to malloc it, and then we try to free it, that will cause problems. So in the context of what is being passed into process, different things could happen, but end of story, we're mallocking something we're freeing something that hasn't been mallocked, and that's going to cause errors. Okay.
Also, the syntax, is it the same? Like, for instance, int star A and then int star A, like it's the same thing. Those are both pointers.
I'm saying it could have, yeah, but to be being passed into process, it could have been a pointer that's being mallocked and passed into process, or it could have just been like, it could have been a local variable that hasn't been mallocked, and then we passed in the address of that into it. So now we're trying to malloc a local variable, or sorry, free a local variable, and that's going to cause issues.
Okay.
Because we haven't mallocked it yet. Basically, you can only free stuff if you've mallocked it. So what about 6E, this next section? Sorry, one. Oh, whoops, have me reading chat. So this guy is going to be interesting because let's go over this and let's just ignore magic for now. So we're getting int star R by extracting it. So int star R, we're mallocing it, we're setting it to a value, and then we're returning it. So we have a mallocked pointer here, and now we're freeing it. So that's good. But we don't know what magic is doing. So it could be it could be holding on to a copy of the pointer, and then we're freeing it. And so then if, like, say if magic saves R as a class variable, but now we freed it. So then when we go to try to use it, we have a dangling pointer. Or if magic frees it, then we're trying to free it again, which is, again, bad. So two cases that could happen right here. Does that make sense? Everybody Gucci? What do you mean by use case for ref counting?
Like, is this a use case for ref counting? Because we're now calling and we're now going to go into some other function somewhere that's going to use our pointer.
Yes, exactly. So this is a good, yeah, this is a good example of where you should be using ref counting. Okay, so then now we have this last one. Yeah, so this is good now, right? Because we're just passing an integer into it. We're not passing the pointer into it, so it can't do anything funny with it. We're just passing in its value. And like we said last time, we went over this without magic, and it's good. So if we just have magic with its value, then there's no problem. So now we get to move into the wonderful world of ref counting. You know, it could be worse. We could be doing we could be translating assembly into C, which is a nightmare, and I've always been very bad at. But we're not, so we're just going to go over ref counting. So I think I'll link it again. So I made a Google Doc with the class on it, so you guys can go through and work through this. So let's do these first. Let's do A to C first, and then we'll go over what the code's actually going to look like after we fixed it.
Okay.
Okay, for the first three parts, ABC, what do you guys think? What is it going to print when it executes? So for this, we just need to look at the main function. We can just assume that they work like normal stacks. So we're declaring E1 and E2 as 23 and 42. We're pushing E1 and E2 onto it. We're saying that E3 equals what we pop off the stack, and what we just added onto the stack was E2. So now E2 and E3 are the same. Now we're going to push E1 and E2 onto it again. Now we're going to pop off the stack and call that E4. So what we're popping off the stack is E2 again. So now E2, E3, and E4 are all the same pointers. So when we do the print statement, E1, E2, E3, E4, what we're going to print is 23, 42, 42, 42. Okay, so what do you guys think for this one?
Wait, can we have a bit more time to catch up? I'm still actually drawing the memory out.
Okay. We're drawing the memory out?
Yeah, like it just makes it easier to see what's happening.
So with those stack pushes with E3 and E4 in the last few lines, those pretty much are meaningless in terms of the answer to the 7A.
Yes, because we've already established the pointers. But that is important later on, though, for ref counting.
Wait, so is the capacity like, okay, so when you initialize a new stack, we're just saying capacity is 3, index is 0, but then is the data a pointer to a, I guess, an array of pointers of size capacity?
Yeah. Yeah, so it's, yeah, so data is the size of 3, is an array of int pointers, size 3. Or size capacity, which is 3. Okay, so this one you don't, you can just look at the code really quickly and see what the problem is here. So with ref counting, what is the just in general, what do you have to be concerned about when you're pushing something onto a stack? And the stack is a new struct. Oops. And in this context, well, we're not saving it to a class variable, but still we still have to use ref counting. So what's the problem with pushing something onto it? Or like, what do you have to be careful with when you're pushing something onto the stack?
that you have enough space in the array of int pointers?
That's actually not a huge concern because you could, like, you could potentially just keep adding on, and it'll just keep adding on. So like so yeah, that's a concern, but that's not what I'm talking about because I'm talking about specifically ref counting. So what's the problem with pushing something on in the context of ref counting?
Oh, you have more than one reference now to, you know, whatever your E is, E1, E2.
Yeah, so in this, oh shit. I think this is supposed to be, sorry, one sec. I think that I deleted a line when I wasn't supposed to. Okay, so I've added that line in. It's under stack push. So basically, if RC keepref is in stack push, but it's not anywhere else, we're always going to be incrementing the reference count within stack push, and that's going to produce a memory leak because we're not actually freeing it. Oh, wait. Oh, no, that's fine. Yeah, okay. Okay, so why don't you guys, oh, now we're going through 7C. Okay, so have you guys gone through this part yet? So basically, we are, so given that the program implements reference and counting correctly, give the reference counts for the following two objects when printf is called from main. So E1 and E2, they're going to be different values. And if you guys worked out how many times they're going to be called, if keepref and freeref are done correctly. Yeah, that's basically the gist of it. The problem in 7B is we're not freeing the reference when we're popping it. So that's going to cause a memory leak because we're never actually going to free the variable.
Aren't we, we're also returning the result though to wherever it's called. But I guess because I don't see where we're replacing that reference in the data, the array of the int pointers to null.
Sorry, say it again.
So in the stack pop, I know we're returning that pointer, whatever it is, that's stored in the array of ints, like in the data, right? But
yeah,
we're not actually, we're returning that to wherever it's called. So now we have a reference to whatever that was pointing at, but then we're not actually overriding that space in that array of ints, of int pointers, sorry, to null. Is that why we would need would free ref do that? Like it would just get rid of that?
No, if you
Or-
set it to null, that'll always be a dangling pointer. You can't just,
Oh,
you can't just set a pointer to null because the memory is still going to be allocated.
Right, but wait, so we're not going to free it, or?
Well, it's not being freed right now, and that's the problem.
Okay, but if we do free it, would we then also need to set whatever's in there to null?
No, you don't. Not necessarily. If you never use it again, then no. If you do end up using it again, then yeah. So it all depends. In this context, yeah, you should be setting it to null. Okay, so what's the value of E1? Sorry, how many times? Actually, yeah, what's the reference count of E1 going to be? So we're going to have it be 1 because we're calling element new. And when you do element new, it says rcmalloc, and rcmalloc is going to set its ref count to 1. When you push it onto the stack, that's going to add it again. When you add it to the stack again, that's going to turn into 3. And that's it. So the ref count is for E1 is going to be 3 afterwards.
Right. Wait, so that's because we have our E1 that's just pointing to that, and then we
push it twice.
when we pushed it twice onto the stack. Okay. What about the E3, the stack pop?
Well, we're not talking about E3. You're talking about we're talking about E2.
Right, but E3 is stack pop of S. So
yeah, and
isn't that also pointing to E1?
No, it's pointing to E2. Stacks are Philo.
Oh, okay.
First in, last out. Okay, so E2. E2 equals element new. Stack dot push. E2. That's going to ref count it again. E3 equals stack pop. Still 2. We're going to stack push E2. And then we're going to stack push E3, and then E4. I know that there's a typo in the midterm. I think this is the one where it was a typo. They said the answer is 4, but I think it should be 5. Because we have we have E2 equals element new. We're going to push it onto the stack, and then we're going to push it on the stack again, and then we're going to push it on the stack 2 more times. What it calls E3 and E4. Those are remember, those are all E2. They're all equal. So when we do element new, when we push E2, when we push E2, when we push E3, and we push E4, that's all going to add a ref count. So the ref count for E2 should be 5.
Do we not add another, like, more ref counts when we push E3 and E4 again? Because aren't those still just point? Okay, maybe I.
Yeah, so element new, push E2, push E2, push E3, push E4. That's 5. Wait, hold on.
It shouldn't have a account taken away when you pop it. Like if it was implemented, the ref count was implemented correctly, it should have a, you should take one away and pop, right?
I think. So if you Well, actually, that's up to you guys in your implementation. So 7D now is actually do the implementation for the ref counting. So there's multiple ways you could do this. I think there's multiple ways you can do this. There is one best way, but I think you could get away with doing this multiple ways. So why don't you guys take a few minutes and try to work this out, because this one is tricky to get the free refs exactly where you want them.
Oh, I just noticed there's actually a limit on the capacity where if yeah, like you can only keep adding it in as long as the index is less than the capacity. So you can't actually have more than a certain number of like pointers stored in the array of pointers.
Oh, yeah, you're right. How about that? So that actually makes sense why the answer actually is 4. Because when we try to add oh, you can't see what I'm highlighting. When we try to add stack.push E4, it's going to do nothing, and it's not going to add to the stack. So the answer actually is 4, not 5. That one is very contentious. Like 90% of the students got that one wrong on the midterm, I remember.
Sorry, that was because when the stack was initialized, it can only fit 3 and not
Yes.
4.
So we push. So if we're ref counting for 2, we push 1 and then we push 2. So now we have two elements on the array, and the ref count is 2 for E2. We're going to pop it. We're going to push E2. We're going to push E3. Now the ref count's at 4, and we're at the max for our array. We're going to try to push E4 on it, but we can't actually push it. So that just means that we're going to do nothing. And now the ref count is 4 for E2. Okay, so let's take a look at stack delete. So what are we going to be doing for stack delete? What lines are we going to be adding in?
Sorry, to stack delete.
Yeah.
Probably freeing all the E1, 2, 3, 4.
Well, what exactly are we changing? So we have while s index is greater than 0, stack pop, and that's it. So what do we have to be adding here?
A counter for our index.
What do you mean by counter?
Actually, wait.
Like
No, you're right.
incrementing
We don't
it
need
down.
to. We don't need to change it because our index is incrementing in the pop function.
Yes. So we should be adding RC3ref on around stack pop.
Okay.
Alternatively, I think you can get away with putting RC3ref into stack pop, but let's put a pin in that for 1 second. Let's go over their solution because I'm sure they have it this way for a reason. So if we put RC3ref around stack pop, that means every time we pop it off, we're gonna say the stack's not using it anymore, and then get rid of it. Then what else do we need? Because keep in mind we're deleting the stack, and if you scroll up to the stack initialization, we are mallocking it.
So we have
So
to
yes.
free the actual stack. Right?
Yeah, so if you look at stack new, it says struct stack s equals rc malloc size of struct stack. So yes, we are mallocing the actual stack, and then we're saying s data equals rc malloc size of instar times capacity. So we're mallocing two things here. So first we're mallocing the stack, and then we're mallocing the data. So in reverse, when we're deleting it, we have to free the data and then free the stack. So the two lines we should have be adding in there is RC3ref. Which I'll add in the Google Doc so you guys can see. Is it just s dot data, s2 data, and then RC3ref s. That make sense? And then we're going to be RC3refing Okay, so now what about main? So we're establishing all these elements, right? So let's look at a basic case. Let's say we're just establishing E1 equals element new, and we're adding it to the stack. At the end, when we call stack delete, it's only going to ref count it once. So its ref counter is still going to be at 1 when it's gone, right? So what do we have to do here to correct that? I'll give you a hint. It starts with RC3ref.
Sorry, would you mind explaining again why it still has a ref count of 1? Oh, because at the very beginning.
Yeah, so you're calling
Okay.
element new, and then you're adding to the stack. When you add it to the stack, now the ref count is 2. When you delete the stack, it decrements the ref count by 1, but we still have 1. So because we're using this in the main function, basically what we have to add is RC3ref on all 4 elements. Let's highlight those, change them a different color. So the stuff in blue
Okay.
is the stuff I added.
Wait, is this because when we initialize the element, we have an RC malloc, so we're having a count of 1. But then when we were pushing these elements to stack, that was an additional 1. So we only really got rid of the ones we were pushing to the stack. So we still have to decrement the references to the elements right before we're done.
Yeah, any like if you're mallocing something, you have to be decrementing in the function that you called it in, always. So we have to RC malloc it when we're using it, like in the stack. So that's why we free ref when we're when we're calling stack delete. Because if it's in the stack, that means that it's being allocated, and then it's also being incremented when it's being pushed to the stack. So you have to decrement it when you're deleting the stack, and then you also have to delete it when you are like when you're done with the main function. And that's it. So this is the answer they have. Let's see if we can't figure out why. Because I know a lot of you guys, you probably think that you should add in the free ref when you're popping, right?
I was wondering that, yeah.
And that would be my first inclination as well. So let's see why let's try to figure out why they did this way. So if they have free ref when you're popping, that makes sense. So then what you do is you would get rid of the RC free ref when you're calling stack delete. Okay, so let's go over the main function and make sure that this works. So E1, ref count 1. Actually, I guess I can go like this now. So E1 is ref count 1. When we push it, now it's ref count 2. We push it again, now it's ref count 3. Now we free it to ref count 2, and then let's just pretend that that's in there. We pop it twice, so now it's ref count 0. So that's done correctly. So what about number 2? Okay, so we add it to the stack. Or sorry, we wait. Can you guys see this? It doesn't have a green. Can you see the document?
Yeah, we can see it.
Yep. Yeah.
Okay, weird. It just doesn't have a green box around it, which it usually does. Anyway, so int e2 equals element new, so it's ref count 1. We're adding it to the stack, ref count 2. We're popping it off the stack, so it's ref count 1. We're going to push it to the stack again, ref count 2. We're going to pop it from the stack, ref count 1, and then we're going to push it twice. Sorry, we're going to push it one time because the stack's full now. So now it's ref count 2. And then we're going to pop it off the stack when we're deleting it. Oh, sorry. First, we're going to call free. See, here's the problem. See, now when we free ref it, it's going to be freed right here.
But isn't this free ref here just because we don't have the free ref in pop? Wouldn't we not need this if we had
no,
free
this
ref
one
in
is
pop?
this one is here because we don't have it in pop. I think what we can do here is actually get rid. In this case, if we want to do it that way, we can get rid of these two because we're not actually declaring element new for these guys. Yeah, so this is a kind of weird way they've done it. So the way they've done it is they've done it instead of putting the free ref in stack pop. What they've done is they've assumed that when you're calling a pointer, now you should be free refing this specific pointer when you're done with it. It's kind of strange because all these pointers are equal. They're all pointing to the same thing. So what you could do is you could actually get rid of these two because these are basically just local variables. You haven't called element new on them. So we get rid of these two and then get rid of this one and then just put it in stack pop. Now this is going to be correct. So it looks like there's two ways to do this. Does that make sense? Probably not.
Yeah, I think it does, but I don't feel super comfortable with reference counting. So
it's if you have a question like this in the midterm, yeah, it's tough. Like so when you do your implementation, you want to make sure that you actually go over the code and just make sure that all your ref counts are 0 at the end of it. Just because that's the most important part. And if you do, you probably have the right answer. So the way they have it here, it's going to get the right answer because they're calling free ref on these new variables. I wouldn't do it that way. I would just treat these as local variables and only do ref counting on the actually that is a bit tricky because they are equal, but they are adding them to a stack. No, I think in this case it's okay to do them either way. Watch me get ripped apart by Feely because there's something wrong with that.
When you say either way, what are the two different ways to do it?
So one way is this way. So they don't have it. The reason they're doing it this way is they don't have it in stack pop because they're calling free ref in the delete function, and the important part is they're assigning this to an int pointer, and then they're freeing it down here. So this is kind of weird because you could just call stack pop without assigning it to a pointer, and then you're going to have a memory leak. So in their specific implementation, and you're going to have memory leak because let's say you add E1 to the stack, and then you just call stack pop. Now when you delete the stack, there's nothing in the stack, so you're not going to call RC free ref on it, but your ref count is still 2. So when you free ref on E1, now your ref count's 1, and now you have a memory leak. So this is very strange that they did it this way because in their implementation in main, you're not going to get a memory leak. But if you just call stack pop, then you will get a memory leak. So it's strange that they did it this way. I think the way that makes more sense is to just put it in stack pop and then treat these as local variables. So you wouldn't have these here, because then when you push it onto the stack, you increment ref count. When you pop it off the stack, you decrement ref count. That seems to make a lot more sense to me.
Wait, what were the counts again for E1 and E2?
3 and 4. And the reason it's 4 and not 5 is because the size of data is 3. And so when you push this onto the stack, it doesn't actually add it onto it.
But this, I only got 3 and 4 when I did it such that I had the free ref in the pop. So I'm wondering, because if the free ref's not in the pop, will you get a different count?
That's a good point. Yeah, let's see. So yeah, you would get a different answer.
That's strange because their answer does not have free ref in the pop function. Or
yeah. So I think what's going on in this question is maybe it's just not a very good question. Like there might be some very small detail I'm missing the why they had it this way, but my understanding, it looks like they could do it this way. I remember there being a huge kerfuffle because like I said, 90% of the students got this one wrong. So maybe we can look at a different ref counting example, just go over it really quickly and talk about it because ref counting sucks and it's really hard. Because all that's left on this exam is just static flow stuff, which you guys are not doing. So I have the 2018 Winter 2 midterm, 2019 Winter 1, and the 2019 Winter 2. I think you guys all have all 3 of those.
Yeah, the 2018 Winter is a pretty good ref counting question.
Well, I got this off. Let's see. Oh God, there's if statements in here. Where's the actual code? This looks terrible. I don't want to do that. You said 2018 Winter 1?
Yeah, 2018.
Oh, this also looks terrible. Okay. not quite as terrible though. Yeah. So first off, the thing I would notice right away is you have these two. Can you see what I have here? Can you guys see? Can you see the midterm I pulled up?
Yeah, we can.
Okay. So they're adding free ref here because they're adding keep ref twice. So they're adding keep ref here, and in the main function, it makes sense that you would have to call free ref twice. Oh, but they are doing it right here. Let's see why they've done it this way. Oh yeah, okay. So when you call b underscore get, that's going to increment your ref counting to 1, I assume. Okay, I got to take a second and look over this because I haven't seen this one. Okay. So what they're doing here is we're initializing b, which is just making an array here at size 4. So in 0, we're putting a create. A create is calling RC malloc, and we're returning that value. Or we're setting that value to I and then returning that value. So now in zero we have an int pointer. We have an int pointer here. Then we're calling b put, and we're getting 0, which is just going to return. Why do they have a function for that? Why don't they return it? Anyway, so then they're going to put a 0. Sorry, b0 into 2, and then because a0 is in 2, we're going to be getting a0 again, putting into 3. So in 0, 2, and 3, they're all a0. They're all let's call it a10. This value is in a 0, 2, and 3, and then this guy is only in 1. So over here, they're doing some weird stuff. So they're saying if So when they're calling b put, they're saying if the index is within the is within the bounds, we are going to okay. So if the index is out of bounds, we're just gonna do nothing. If the index is in bounds, then we're gonna say if the value of b at that index exists, we're going to call argc free ref on the values, because now we're putting it because we're putting it into b, like we're taking it from where it was before and then putting into b. Then we're storing value, the pointer that we passed in, at that index. And then if that value is not null, we're going to increment the ref count. So this is just kind of getting around null, essentially, because if you pass in null as value, or b doesn't have anything in it yet. So when we call b put for the first time, there's actually nothing at 0. So we're going to check if b values of index 0, and that's going to return null. So we're not actually going to free the reference. Then we're going to assign b0 equals the value, and that value is a create 10. So that's just creating an int pointer size 10, or sorry, with value 10. And then if the value is not null, we're going to increment the ref count. And so now this pointer here, its ref count is going to be 2, because when it calls RC malloc over here. So right here we have the ref count of 2. Now we're going to do the same thing, except it's going to be in index 1. So and this time we're going to call b put 2 in b get 0. That's just going to return this first pointer, whose ref count is at 2 right now. So we're going to say if index is good, it is good. If b values index exists, it does exist. So we're going to increment the ref count. So now this ref count is 3. We're going to assign that value to that index.
I think it frees it,
Oh.
so it frees whatever was previously there. If that, I think, like, it's weird. They assume that the array was already occupied by something. I think that's why the free is there.
Yeah, exactly. So yeah, I misspoke there. So it's calling 2, so it actually is going to be null. So the b values of index doesn't actually exist. But if it did, because we're overwriting it, we would have to free it. But that isn't the case. So we actually never go into this if statement. But yeah, you're right. Because like there's possibility for this int pointer to be overridden. So you would have to free it. But otherwise, we add it to the index and then just increment it. So now the fun part is freeing up all this stuff afterwards. Because we called bget, if something is in b, that means its ref count is at least 2. Because we've created it, which makes the ref count at 1, and then we put it, and we just saw that when we put it, this is going to increment the ref count to 2. So when we say this int star p, this is going to be at ref count at least 2. So that's why you need to free it twice afterwards. Does that make sense? I know, ref counting sucks. And the reason they're putting all these into null is because when you don't want to, this is kind of like the delete function last time. So we're going to be putting all these values in because otherwise there's going to be dangling pointers when we finish the main function. So this is just going in here, and now this is saying if the value exists, we're going to free it.
Is it possible that?
And then we're going to be putting null into here. But then null, so we're not going to be doing the second if statement. Sorry, what was that?
So I've heard from some friends of mine that took this course like last year. Apparently they made it on the first midterm. Like just from this, it seems pretty fair. Like ref counting is not that much, like not a huge chunk. But
it's impossible to say, really. Yeah. It could be a huge part, it could be nothing. Ref counting wasn't, I don't think it was on the midterm that I invigilated last time. Oh no, I don't have that one. Oh, I do. Oh no, it was. Yeah, I don't know. On all the midterms I've seen, they're having ref counting, so I think it's pretty likely that there is. But you never know. At least you guys are lucky that you aren't doing any like while loops or anything yet, because that's really damn complicated. It's very annoying. So the moral of the story is you have to be really careful about when a structure is going to be using a value. So if something is going to be using it, you have to increment the ref count, and when it's done using it, you have to decrement the ref count. So in that stack problem, when you're pushing it onto the stack, you should be incrementing the ref count, and when you're done using it, you should be decrementing the ref count, either in stack delete or when you're popping it. I think both make sense. So how do you guys feel? I know ref counting really sucks, and it's very confusing. My biggest tip would be, if you have time, I'd probably leave that till the end, because it can take a long time and it can be really confusing. Go over it and just make sure that your implementation returns for each pointer that's been allocated. Just make sure each pointer is returning 0. Just do the counts for each one. Go through the code and see what the counts are. If the count ends up being like 2 or something, then clearly you've done something wrong and you're gonna be missing a step. Is there anything else you guys want me to go over before we're done here? Okay, well, I will stop recording then.
I was wondering if I could ask like a specific question from a midterm.
Sure, yeah.
I think it's
I think I have all of them, so I can pull it up.
I think it's 2019 winter 2. Yeah. 2019 winter 2, 5C. I think it was like about the syntax, because
What?
it was something, it was just like the syntax of pointers.
My computer's all weird. What the hell is happening? Um, 2019 winter 2.
Yeah, 5C.
Okay, well, my copy has do not share on it, but if you guys have a copy, then I had this when I was a TA. So if you guys have the copy, then I'm sure it's fine now, hopefully.
Yeah,
so
we have all the solutions. And
okay,
stuff,
good.
yeah.
And I'm not breaking
So-
any laws.
So
this guy-
it's pretty straightforward. So like when it's like C and C is a pointer and it's C equals B plus 3, because C is a pointer, when you grab the value of B, are you grabbing the integer value of B or the address value of B? Because it seems like it does the same thing for 5A, where it's D equals C minus B. And it seems like the value you grab when you grab C versus the value you grab when you grab B is different based on what's on the left side.
yeah, it's weird.
Like so like D is an integer, so it's like you take C, which is a pointer,
Yeah,
minus.
the reason is, wait, sorry, where does it add just 1 to it, like you were saying?
What do you mean just +1?
Because you said in this case we're adding 12, right? We're adding 12 to B.
Yeah.
In
Well, it was
what
more,
case-
it's the value of B. So like when it's C equals B, when it's grabbing B, it seems to grab the address of B. But then in
Yes.
5A, when you grab C, you
Okay,
actually
well-
grab like the value of C and
well,
not
look
the
up here
address.
and tell me what B is. Is it an int?
Yeah, like that's what I was wondering is like, so if it's like C equals something, because C is a pointer, when you grab the value of B, are you grabbing the address just by default?
No. Well, let me explain. So it doesn't matter what C is. So C could be an int, it could be an int pointer, it could be an int double pointer, doesn't matter. But the important part is B is a pointer. So the value of B is an address, right? The value that address points to is an array, but the value of B is an address. So the address of B is one thing. The value of B, which is an address, is another thing. So there's 2 addresses with a pointer, and then the pointer, or what the pointer points to, is another thing. So there's like 3 values that could be associated. With an int, you have the address of the int, and then you have the value of the int. But for an int pointer, you have the address of the pointer, whose value is an address, and then the value of the pointer, which is an integer. Very confusing. So in this case, we're saying b plus 3. So we're taking the value of b, which is the address of A0, if I'm not mistaken. Wait, hold up.
That's why I was a bit confused, because the answer is like it's 2000s, or it's 200C.
Well, C part makes sense because you're adding 3, and because b is an int pointer. So if b was just an integer and its value is like 6, then yeah, you would be then you would be adding like 6 plus 3. But because this is
It seems to be taking the address of b, adding 12, and that's the answer.
Yeah, so this is where C gets really just kind of annoying. If this was b bracket 0, then it would return the address of A0. But because it's just b, what that does, because C is very annoying, is returns the address of b.
That's why I was confused, because in 5a, when it's d equals c minus b, when it grabs the value of c, it grabs the address b1. But then when you call b down here, it fucking grabs the address of b, which makes no sense, because it's
Dude,
like the
I
same
know.
syntax.
I took this course. I got an A in it, and then I TA'd the course, and I still don't understand C sometimes. There's just some things that you just have to remember. Like in this case, that's what C does. C is just a pain in the ass, and it has really weird things that it does, and that's one of them.
Yeah, because why I was trying to find the difference is because like I wasn't sure if it mattered what was on the left side. So since C was a pointer, it would grab like the address of B just by default. But in 5a, it's looking for an integer, so it goes and finds like the address of B1, which is 2004 or something, and then it minuses off.
Oh,
B.
okay. Sorry, that is why. Okay, yeah. So in this case, D equals C minus B, and that's
Yeah.
So what's C in this case? Oh no. Okay, sorry. No, I know why. Okay, so C equals. Can you guys see my mouse? So C equals B1,
Yeah.
right? And we're saying D equals C minus B. So C minus B is in this case, what it's doing is saying B1 minus B0, but the addresses of them. So it's like the address of B1 minus the address of B0 is one increment. So it returns 1. It doesn't return 4. It's 4 bytes away. So B1 minus B0 is 4 bytes, but it's one like increment. That's why it's the same thing down here. Like when you say B plus 3, it returns the address of B plus 12 because it's a pointer. So because this pointer is one increment away from B, D equals 1. Does that make sense?
But it was just how, so like, you know, when it finds the value of C there, it actually grabs the value that C is storing, which is the address of B1. But when you go and grab B down in 5C, you grab the address of B, which is a different, like it's a different step, I guess. Like it doesn't grab the value that B is storing. It's grabbing B's address, which I was wondering if that's specified by because C is a pointer, it grabs the address by default. Because when I wrote it in C and did a quick test, apparently that's how it works. But like here, it just seems really hard to differentiate.
Yeah, honestly, I don't really know what to tell you. That's just a rule of C, and that's just what it does. I wish I had a better explanation. C just does really weird things. Yeah, it seems like it should be 3,000 minus
like yeah, my original answer was like you go and take the first value of B, which is the address of A0, and then you know plus 3 to it, and it would be 1.
I want to say my best guess is because C is a pointer and B is a pointer array. So when you say the value of B, you're not specifying B0 or B1 or B2. You're specifying but then in D equals C minus B. No, I think that's right because you're not specifying that C is an array. So when you go down here, it's just the value. So you're saying the value of C minus the address of B. Yeah, that's not a very good explanation. It's that would be my best guess. It's because C hasn't declared to be an array. But B, no, that still doesn't make sense.
There were like a lot of typos in some of these, like on PS, that there were post after post about typos. So I wasn't sure if it was a
Yeah.
typo, but
Yeah,
or if it's specified by left hand side. I have no idea. It just
yeah,
didn't make sense.
it very
when I
well
was
could
doing
be. If you check, if like my best thing to do is just check in C and see what it actually does. But I know that C does really funny things. But yeah, most of the time it's if you're dealing with an address, you're always going to multiply it by the size of the address, because this is basically like incrementing the position. In this case, that's really weird, and I don't know, maybe that is a typo.
Does it like, because the value of the C minus B is 1, is that because D is an integer, it's knowing what to expect on the right hand side? Like, does that change anything depending on what's on the left hand side, or does it not matter?
Can you say that again?
Like for D equals C minus B, D is an int. So
Yeah.
is D expecting an int? So when you do, B1, which is 2004, and then you're minusing it off by 2000, so 2000 minus, or 2008 and 2004, whatever it is, and then you get like pretty
Yeah.
large.
So it's kind of like this, but but in reverse. Like when you're incrementing an address, it's incrementing it. It just automatically multiplies it by the size of whatever it's pointing to. So this adds 12, and conversely, these two are addresses. So it's going to be equivalent to the difference in positions of the addresses.
Generally, like I think the actual, like if like arithmetic wise, it's larger than 1, but I think it's like 4. Like the difference is like 4 or something, but then you just bring it down to 1 just based on like the alignment size.
Yeah, so it's 4 bytes. Yeah, it's four bytes, but it's one position, because it's like you said, it's an int of size 4.
How should we interpret that? Like the star C equals address B of 1.
Well, that's saying that star C
Referencing the pointing that you're pointing at.
So star C equals A of 2, and star C equals 4, right? So
Okay.
that's if you dereference C twice, that's what it's pointing to. So it's basically saying that A of 2 is going to equal 3, and that's what it's saying here. So OX 1008, which is this position, and we're overwriting this to be 3.
Yeah.
And then this one, we're saying D equals, for some reason, the value of this minus the address of B.
Wait, so which exam is this? This is the winter term 2?
Winter 2.
Okay, that's a good one. Oh man.
Yeah, and this could have been before this is the copy I got when I was invigilating the exam, so there could have been a typo in this for sure. But you have the same copy, so.
Yeah, it's the same copy with the same answers, and even our solution page has the big do not share on it too.
Oh, how about that? Okay, so you probably have the exact same one.
Yeah, but just like, I just didn't get why B was the address of B. It just didn't make sense, and not the value of B, because I thought you would actually have to put like the address, like the ampersand in front of B if you wanted it to do like the address.
Yeah, I'd say just open up C and actually do and just try it out in one of your programs. I would, but I don't want to set up IntelliJ right now, so I'm not going to. What about the rest of these? You guys, do these make sense?
Those, like I went through this exam, those were the only, like those two together, like the D equals C minus B made sense, and then when I hit that other one, I just didn't get it. So that was the only one that I had problems with.
Yeah, that's weird. I'm not informed enough to give a concrete answer on that, unfortunately.
The
approximate knowledge of like 8 of these courses. I think I have like I could probably like write any of these exams and get like an 85. So like there's sometimes I'm like, try my best. It's hard when sometimes like when people are asking me about 221 questions about like, I'm gonna stop the recording. People ask me questions about the 221. Where do I stop?